So, good evening, class. I hope this video finds you well. This will be our 11th video, and you'll be watching this on Wednesday night, I believe. So, this circle's 11, and we are continuing our work on section 10.5 out of the textbook, out of this unit. And our goal today is to talk about tangents drawn from a point outside a circle. And so there's a theorem, and the theorem is going to say the following things. If I draw a tangent from point P outside the circle to where it touches the circle, and then I draw another tangent from point P so that it also touches the circle in one point, then those two tangents are equal. So both of those tangents are going to be the same length. And so you could say it this way. If I have tangent PA, tangents PA and PB to circle C from point P outside the circle, then PA is congruent to PB. And that's the theorem. And so there are some really cool problems we can do with this particular theorem. So we're going to start setting those up. So before we start doing problems, I want to talk about an idea called circumscribed polygons. Now, we've already talked about inscribed angles, inscribed quadrilaterals, inscribed triangles, and those were always inside the circle. So circumscribed means that they're outside the circle. And so a circumscribed polygon would be something like this triangle, like that, or it could just be a quadrilateral, like this. Or it could be any other polygon. It could be like a pentagon or a hexagon or anything else. And all of these are circumscribed. Now, the key characteristic of a circumscribed polygon is that each side is going to be tangent. Now, my drawings are a little rough here, but the general feeling is that I was trying to make them touch at only one point and be tangent. And so you can see that a triangle, because it has three sides, is going to be tangent in three spots. A square, because it has four sides, is going to be tangent in four spots. And a pentagon with five sides, tangent in five spots, etc., etc. And so it won't be circumscribed if you have something where even though part of the polygon is tangent, like this triangle, it's tangent here or tangent here. This side is not tangent. It actually crosses the circle in two places. So this would not be circumscribed. So circumscribed means that it has to be tangent everywhere. All the sides have to be tangent to the circle. So here's our first problem. What we're doing is we have a circle, and we have a point P outside the circle, and then it's apparent that we have drawn two tangents to the circle. PQ, tangent at point Q, and PR, tangent at point R. And so the theorem tells us that if you have two tangents drawn from the same point outside the circle, then the two tangents are congruent. So the first thing we can say is we can say PQ segment is congruent to PR. Well, and because they are congruent, that means PQ must equal PR, and so that means that these segments are equal, so I can substitute 2x is equal to 6x minus 4. Solving, subtract 6x from both sides, and I end up with negative 4x equals negative 4, and I divide by negative 4, and therefore I get x equals positive 1. So in this case we have solved for 1, and then if you were asked to say, well, what's the length of PR, then you would substitute 1, 6 times 1 minus 4, and you would find out that PR is 6 minus 4, or equal to 2. And if there were units, then you would attach the units to it. So that's the basic problem, and those are pretty typical. So now what we're going to look at is a slightly more complicated problem. So looking at the black diagram here, what we can see is that from point X I've drawn two tangents to the circle at point Y and Z. And I have told you that the line from X to Z is equal to 17 inches. So what does that mean X to Y is equal to? Yes, that's correct. It is 17 inches as well. It is this little fact that we are going to use to help us to deal with some circumscribed polygons and their lengths. Now I'm going to finish this diagram, and I want you to think about this and how we got it. And this diagram is going to be changed a little, so you'll see it when we come back. So for our final example problem, here, what we have here is, you can see, here's the 17 inches, just like I had up here in this diagram. Now notice from point B I've drawn two tangents there and to there. So if this piece is 17 inches, then what should this piece be? It should also be, that's right, 17 inches, just like it was up here. So given that particular fact, I know that this piece is 17 inches, going right to there and going right to there. They have to be equal because they're tangents from the same point outside the circle. Now given that, if this is 17 inches to the red dot here, right, then, and the whole distance to A is 27, that means this piece must be 10 inches. And now we're playing the game. Notice from point A right here, we have a tangent to right there and a tangent to right here, but they're from the same point, so if this is 10 inches, then this side here must also be 10 inches. And so those two sides match. And now we can come down here and we have to solve the rest of the problem. And I'm just making sure I copied it correctly. Oh, I forgot one thing. Pardon me. I forgot this. That's why I was concerned. This is 11 inches right there. And so since it's from the same tangent right there, that means this must be 11 inches. And then there's 11, there's 14, and our goal was to solve for x. That's one thing. X is this piece here, but it corresponds, because they're from the same point, two tangents. And so therefore I get a little equation, 14 equals 2x, which gives me 7 is equal to x. And so now I've solved for x. And the other problem we usually are trying to solve here is, what is the perimeter of the circumscribed polygon? And in this case it's a quadrilateral, so what would the perimeter be? Well, you would proceed then to add things up. I'd have 34 plus 20 plus 22 plus 28, and when I added those up, I'd get 104 inches would be the perimeter. And so that's a typical problem. So on the next slide, I'm going to have you do this yourself, and then you should be ready to come to class tomorrow. Okay? So here's the last problem, and there are three things that I want you to do. I want you to find x, I want you to find y, and I also want you to find the perimeter of the pentagon. So look at the problem carefully. It's a combination of the first theorem about two tangents being drawn from a point, and also similar to the last problem we did with the quadrilateral. So good luck, give it a shot, and then pause the video, come back, and see how you did. So I know that from C, this line and this line have to be equal because they're from the same point. So I can say 4x equals x plus 9. And therefore 3x is equal to 9 and x is equal to 3. Using the same strategy, I can say 2y equals 10, and therefore y is equal to 5. And so now I have both of those, but I want to help myself with the perimeter, so I plug y equals 5 in there and I get 10. I already have 10, and then I plug 3 in and I get 3 plus 9 is 12, and then 12 here. And now I got to do this part over here. What I notice is this segment is 3, so this is a tangent from the same point, so it has to be equal. So I need that 3 and this 3 in my perimeter. And then this segment is 4 right here, so this one must also be 4. But the whole thing's 12, so that means this one must be 8, and therefore this is 8. And now I think I have everything, and all I have to do is add those up. So the perimeter is equal to 20 plus 24. Notice I'm doubling these. Plus 6 plus 8 plus 16. And once I add that together, 44, 58, 64, the perimeter will be 74 units. Alright, so good job. I'll post this video today and you should be ready to go when you watch it Wednesday night.